ASME Section 9 Overview Part 3. This is Part 3 of my deep dive. Like I said before, I poached all this stuff from the Nuclear Regulatory Commission Introduction to Welding Technology and Codes courses, and then I just kind of built off their framework. My name's Gary Pace. I'm a professional engineer in CWI out of Katy, Texas. Just like to give a quick shout out to those of you viewing and those of you that are subscribers. About 68% of my or 70% of my watch time on my YouTube channel comes from the guys in India. I really do appreciate that. The other 30% is the United States, and the rest of the world is, a couple of percent. So on the watch time. Rest of the world, I appreciate you guys too, but I'm just giving a shout out to India and the US because they're about 99% of my watch time and view time. So, anyways, thanks guys. I do appreciate it. You are noticed. Acknowledgments. This is where I snagged most of the material from. Most of the other, and if I didn't reference it, it's also from some military manuals. Iron Worker 3 and 2, which is a Navy manual, and a couple other Army manuals that have a lot of information on welding and non-destructive testing. Part QW, welding. So Part QW for welding of ASME Section 9 is broken up into 5 articles. Right now we're just grinding our way in a slow grind through Article 1, which is welding's general requirements. This is the foundation that sets the table for being able to qualify procedures, personnel, or using a standard welding procedure specification. So this is the foundation. This is the foundation of your house. Which we're going through. A lot of definitions in here and concepts and thoughts and all that kind of stuff. Article 1, welding general requirements. Like I've said, kind of give you a rehash. This is setting the table so that we can have the vocabulary and understanding when we go into Articles 2 and 3, how to qualify weld procedures, procedure qualification records, and to qualify welders. So that's what we're doing in this part of QW in Article 1. Destructive testing. In procedure qualification testing and welding development work, mechanical test specimens are removed from a test specimen to check the quality of the weldment. These tests are used to determine mechanically the properties of the weld and base metal. Mechanical properties of materials are measured by a variety of mechanical tests that simulate conditions materials must stand while in service. The most common of these tests are the tension test. This test measures the tensile load carrying ability and the amount of deformation a material can withstand before rupture. A hardness test. This test measures the ability of a material to resist indentation or penetration. Charpy V-notch test and fracture toughness test. These tests measure the ability of a material to resist fracturing in the presence of a notch or a crack. The creep test. This test measures the amount of continuous plastic deformation of a tensile specimen over a period of time. The fatigue test. This measures the ability of a material to resist breaking when subjected to a fluctuating or alternating load. QW 140. Here's where we start kind of getting into the nuts and bolts of the whole weld material testing in qualification of weld procedures and welding qualifications. QW 141 covers the mechanical test, tension tests, guided bend tests, fillet weld tests, notch toughness tests, and stud weld tests. So we're going to go through these, some more in depth than others. Tension tests and guided bend tests. The first two here are the backbone of welding procedure qualification, because almost all weld procedures you're going to have to do 4 side bends or root bends, or you're going to have to do a number of bend tests, guided bend tests, and you're also going to have to do 2, 3, 4, depending on what you got going on, tension tests. Various codes are going to call out what's needed for what. So this is the backbone of weld procedure qualification testing, is the mechanical testing. So you're going to make a test plate, cut it up, machine out some tension tests, cut out some guided bend tests, and evaluate how your material did, your deposited weld metal did against the requirements and expectations for that specific material. Types of loading. So the material properties that we're looking at are tensile. You can see up on the top, we got the two horses trying to pull whatever it is apart. That's a tensile test. We're not going to worry about shear testing or compressive strength, elasticity. The other one we're looking at is ductility. This guy down here bending a railroad tie like he's Superman, right? In E. Those are the ones we're going to worry about. Those are the two biggies. Sometimes we have to worry about notch toughness if another welding code throws us over and says, hey, you got to worry about notch toughness. But for the base, I guess the base situation, tensile testing and ductility is what we're looking for. We want to make sure that weld isn't going to crack because it isn't ductile enough. It doesn't meet the ductility requirements for that material. And we want to make sure it has the tensile strength to hold up under a specific set of operating criteria. Visual examination. Visual inspection is the first method used when inspecting a weld for soundness. It must take place prior to, during, and after welding. Many standards require its use before other methods because there is no point in submitting an obviously bad weld to sophisticated inspection techniques. Visual inspection requires little equipment, good eyesight and sufficient light, a pocket rule, a weld size gauge, a magnifying glass, and possibly a straight edge, and a square for checking straightness. Alignment and perpendicularity are all that is needed for a sufficient weld inspection. Visual examination, QW144. Visual examination as described in QW194 is used to determine that the final weld surfaces meet specified quality standards. So when you do a test plate or you qualify a welder, first thing you're going to do is look at it. Is this thing acceptable to the acceptance criteria? Yes or no? And then you're going to go on from there. But if you got a bunch of cracks or other defects in the surface of your weld, you're going to want to give it another run, right? Our last slide threw us forward to QW194, visual examination. Performance. Performance test coupon shall show no cracks and complete joint penetration with complete fusion of the weld metal and base metal. So basically telling us that, hey, we can't have any cracks and we've got to have complete joint penetration, and then we can go on from there. This is for performance test coupons. This is for testing welders. You need to keep track of these terms like performance and procedure. Procedure is the procedure, and then if you see performance, that means you're testing a very specific individual to whatever procedure or criteria you're testing him to. Tensile tests. Tensile tests are conducted using specimens cut from a test weld and machined to one of several standard sizes for mounting in a testing machine. Specimens are usually taken perpendicular to the weld, with the weld centered in the specimen as shown in figure 15-6. However, specimens are sometimes taken parallel to the direction of the weld and consist entirely of weld metal. Specimens may have round or rectangular cross sections depending on the requirements of the applicable welding code. The testing machine applies a tensile force on the specimen till it ruptures. From readings on the machine and measurements on the specimen before and after the test, properties such as yield strength, tensile strength, and ductility can be calculated. The primary purpose of the test is to demonstrate that the weld metal deposited by the selected procedure meets or exceeds the minimum values of specified in the applicable code. So basically, you're making a weld, and then you're taking a slice out of that weld and you're machining it down, putting it in a tensile tester, pulling on it and making sure that the strength of the weld metal is equivalent or higher than the base metal. And this tells you what you need to know. You can get yield strength, tensile strength, and ductility out of this one set of tests. So tensile tests are a pretty good tool to have in your tool bag. The tension test. Summary of method. Tension testing of welded joints is done by means of a calibrated testing machine and devices. The test sample is pulled in tension until the sample fails. The significance. Tension test provides information on properties of welded joints, load-bearing capacities, joint design, and ductility. QW150 tension tests. QW152 tension test procedure. The tension test specimen shall be ruptured under a tensile load. The tensile strength shall be computed by dividing the ultimate total load by the least cross-sectional area of the specimen as calculated from actual measurements made before the load is applied. So this tells us how we're going to do tension tests. Tension tests are, once again, the backbone of procedure qualification. So here is the test procedure on how you do it. Tension test, summary of method. Okay, for the tension test, we've got on the left, we've got the test coupon in the loading grips. So to figure out what the stress is in PSI, we'll use PSI because I think in PSI, the American/English system, you take your load, which is how much force it takes to make this specimen fail, and you divide it by the initial cross-sectional area. So 100,000 pounds divided by 1 square inch, it'll give you 100,000 PSI is your stress. Your elongation divided by initial gauge length is the strain. So you take your gauge length and then you figure out how much elongation there was and you divide it by the initial gauge length, and then that's your strain. Pretty easy math, pretty cut and dried. Here's a couple of tension test apparatuses. On the right, you can see a conventional loading system for tensile strength only. This is like the old school stuff from the 1950s. I don't know, 1950s, 1960s. This is what they had when I went to college. And then on the left, you can see a modern loading system that's computer controlled, and it'll give you a significantly larger amount of data than maybe the conventional loading system would. But you'll run across both, just depends on where you're at and what you're looking at. Both are quality ways to achieve the data that you're looking for or not looking for. Tensile test specimens. You can see that we've got an all-weld metal tensile test here. You can see the red dot on the top illustration is where the tensile test was cut out of the weld. And an all-weld metal tensile test is used to determine weld metal ultimate tensile strength, yield strength, elongation, and reduction in area. The reduced section tension test determines the ultimate tensile strength only. Specimens shall be tensile tested in the as-welded condition unless the procedure qualification requires a post-weld heat treat. So what's this telling is that you can't do a weld test, do a test coupon, and send it to heat treat, and then pull the samples, and then and then the samples pass, and then you go out in the field and you're going to use that procedure without post-weld heat treat. If you have a procedure and you use post-weld heat treat, all the welds have to be post-weld heat treated. This slide shows an ASME Section 9 QW150 tension test. So if you get thrown out in the field and you need to qualify a weld procedure and you don't know what size the tension test needs to be, you go and you're qualifying the welders and the procedure, well, in this case the procedure, to ASME Section 9. They've got a little recipe book with pictures and dimensions, and it'll tell you exactly what you need to do. Sizes, what it needs to look like, it walks you right through it. So it's none of this stuff is rocket surgery, and then once you become a CWI, there's information out there that guides you through the whole process. So it's not like you have to commit this stuff to memory. Here's another slide. This one is a reduced section tensile test for pipe. Same thing, it walks you through it, talks about grinding the minimum amount needed to obtain a plane, parallel, face over reduced section. It walks you through everything. Like I said, none of this stuff is really rocket surgery, and you don't have to commit it to memory, but you do need to be cognizant that this material exists and that it's out there and you just need to find it. I don't remember any of this. I just know where to find it and look it up. I don't have it committed to memory in some kind of savant type fashion, but I do know where to find it and go dig it up and, you know, let people know what you want done as far as what tests you need done to qualify your procedure. Here's QW 151.2. It's a reduced section pipe for pipe diameters less or equal to 3 inches. Just be cognizant that different codes have different requirements for tension tests. They're going to steer you in the direction that they want you to go in regards to the dimensions of the tensile test samples that are going to be pulled. And these codes will walk you through it. Once you get used to it, it's not too tough. But just realize that a tensile sample cut from a piece of plate 5 inches thick is probably not going to be the same as a tensile sample cut from a 3-inch piece of pipe. Here you can see a turned specimen, QW 151.3. Basically, you're going to take a slice out of the weld. You're going to machine out this little specific specimen. You're going to put it into a tensile tester, and then you're going to pull it. You're going to measure everything, right? It's going to give you a, you know, an area. You're going to calculate. You're going to put a certain amount of force on until it ruptures, and then you're going to calculate the tensile strength of this specific specimen. Here's QW 151-3 or 0.3 turned specimen. So you can have either a tension test that's a reduced section that's turned, or like the ones we saw on the previous slides. It gives you some different options depending on material thicknesses and configurations and customer requirements. But here's the dimensions for the turned specimens. And once again, none of this stuff's rocket surgery, but if you know where to look and how to, you know, use the document to ask for what you want and how to grade what you've been given, you shouldn't have too many problems. On this one, you can see where there's a full section specimen for pipe for diameters less than or equal to 3-inch diameters. So let's say you do a procedure qualification on a really small diameter pipe, 3 inches or smaller. There's no way you can cut a tensile specimen out of that pipe. So they just break the whole pipe. They just chunk the whole pipe into a tensile tester and pull it apart and calculate what the tensile strength of the material and the welds were from that. So depending on what you're doing and what the materials are, there's different options that you can use. And this is the one for small sections of pipe, small diameters. Tensile test acceptance criterion. Here's for D11 and ASME section 9. D11 is acceptance criteria for reduced section tension test. The tensile strength shall be no less than the minimum of the specified tensile range of the base metal used. Reduced section tension per ASME section 9. To pass the tension test, the specimen shall have a tensile strength that is not less than the minimum specified tensile strength of the base metal, or not less than the minimum specified tensile strength of the weaker of the two materials if different strength materials are welded, or not less than the minimum specified tensile strength of the weld metal when a weld metal having lower room temperature strength than the base metal is allowed, or if the specimen breaks in the base metal outside the weld or fusion line, the test shall be accepted provided the strength is not more than 5% below the minimum specified tensile strength of the base metal. So it gives you some rules there. ASME section 9 gives you a little more wiggle room on what you can do than AWS D1.1. D11 is a structural welding code for steel. So it's pretty specific. You're not going to be welding titanium or zirc or other aluminum, copper, whatever. Whereas ASME Section 9, you can end up welding a wide variety of materials. So it gives you a little more wiggle room or a little wider strike zone depending on what metals you're welding. QW160 guided bend tests. Guided bend test specimens shall be prepared by cutting the test plate or pipe to form specimens of approximately rectangular cross-section. The cut surfaces shall be designated the sides of the specimen. The other two surfaces shall be called the face and the root surfaces. The face surface having the greater width of weld, the specimen thickness, and bend radius are shown in figures QW 466.1 and QW 466.2 and 466.3. Guided bend specimens are of 5 types depending on whether the axis of the weld is transverse or parallel to the longitudinal axis of the specimen, and which surface, side, face, or root is on the convex outer side of the bent specimen. The 5 types are defined as follows. The 5 types of guided bend test specimens. I've only got 2 of them shown here, my apologies. So you can have a transverse side bend test, a transverse face bend test, a transverse root bend test, a longitudinal face bend, or a longitudinal root bend. In this one we have a transverse face bend and a transverse root bend. That means we're not going with the longitudinal axis of the weld, we're going across it. We're going perpendicular to the longitudinal axis of the weld. So we're going to bend one where the root is on the outside of the radius, the outer radius of the bend, and a face bend which will be the face will be on the outer surface of the bend. So those are our 5 types of guided bend tests. Summary of method. The specimens are guided in the bending process by a test fixture that employs a mandrel with a wraparound roller or end supports with plunger. The maximum strain on the tension surface is controlled by the thickness of the specimen and the radius of the mandrel or plunger. Significance. The ductility of the welded joint. Like I said before when we first started and we had the guy bending the railroad tie like he's Superman, ductility. We're trying to see if we can deposit ductile filler metal, weld metal into the weld joint. Ductility is the key here. We're looking for ductility when we're talking about guided bend tests. We're not worried about tension, the tensile strength, or the impact strength. We're strictly looking at ductility of the weld joint with the guided bend test. Guided bend test. Summary of method. The specimens are guided in the bending process by a test fixture that employs a mandrel with wraparound roller or end supports with a plunger. The maximum strain on the tension surface is controlled by the thickness of the specimen and the radius of the mandrel or plunger. The significance. The ductility of the welded joint. Basically, this is going to tell you if the weld joint is brittle or ductile. I've seen welds just snap. They look beautiful and they snap, break like glass. And others, they just bend perfectly. But the guided bend test is something that a welding inspector needs to be pretty intimate with. You really need to understand the guided bend test and where to find the test criteria for the guided bend test for whatever code you're working to. Guided bend test procedure. Specimens shall be bent in jigs. This is a general test procedure, but gives you an idea of what needs to be done. The weld and the HAZ shall be within the curved portion of the specimen. If not, the specimen shall be discarded. Unless otherwise specified, the specimen shall be tested at ambient temperature, and deformation shall occur in a time period between 15 seconds and 2 minutes. Appropriate surface of the specimen according to its type shall be bent such that it is placed in tension. Specimen shall be bent around the correct size mandrel. plunger until the specimen is forced into the die, until a 1/8 inch wire cannot be inserted between the specimen and the die, or the specimen is bottom ejected if the roller type jig is used. When specimens wider than 1.5 inches are tested, mandrel must be at least 1/4 inch wider than the specimen. You'll notice that it says the appropriate specimen according to its type shall be bent. So that's are we doing face bends, root bends, side bends? Also, the correct size mandrel. Certain materials do not get bent. Not all materials. Aluminum doesn't get bent on the same material as an A36 generic carbon steel. There's different sizes for different materials and material strengths. So you need to look at the code and make sure that you're using the right test mandrel / plunger to force the test specimen into the die. But there's different sizes. Just make sure you're using the correct one. ASME Section 9 QW160 guided bend test. All right, here you've got the thickness and dimensions for a transverse side bend test. So it tells you what what sizes you should be cutting it with. If you're using P23, which is aluminum, or P35, all other metals need to be this size. But ASME Section 9, they don't leave you high and dry. They give you very specific sizes and shapes that you need to use for a bend test. And it offers you instructions, and if you just work your way through it, you'll get there. But QW161 is for transverse side bend test. And now here's for transverse face or root bend tests. So if you're going to do a root or a face bend test, this gives you the dimensions. And you can see that P number 23, F23, or P35 has one set of material, has dimensions, whereas all other metals have a different set of dimensions. So if you're doing aluminum or P number 35, you use the dimensions they have there, and all other metals, they have it there. So it's not a one size fit all. You need to figure out what material you're working with and go from there. And you can also see that they've got dimensions for plate and for pipe. So depending on what material form you're using, there's going to be a set of dimensions for each. And here's the guided bend test for longitudinal face and root. So if you're going to do a longitudinal face or root bend, this is your section that you're going to go digging around in. But you can see it's used to test materials with markedly different bending properties, largely different properties between different base materials, and largely different properties between the weld metal and base metal. Here's a bend test jig. You can see they've got, if you don't have one and you need to build one, this is the dimensions you follow, and it'll guide you right through it. But this is the dimensions of a test jig. So, but none of it's rocket science. You're just putting a test sample on a anvil there, and then you're using the plunger, and it's pushing the bend test down through the plunger. Here's a bend test jig. You can see the guided roller jig on the left, and then the guided bend wraparound jig on the right. Like I said, there's two different types. We looked at that in a previous slide, but this gives you a little better idea of what's going on. Here you can see we've got another bend test apparatus. We've got the guided bend test to the left in the black and white picture versus the wraparound bend test jig. So there's two different ways to get to the same point. But here's a couple of additional pictures kind of give you an idea of what we're looking at. This is a couple of versions of the guided bend test. You can see the one on the right is a wraparound test jig, and you can see the one on the left is a plunger type. So you just put your bend test sample up there on the anvil and hit the button, and a hydraulic mechanism is going to push that plunger down and bend your test sample, and then you take a look at it, and if it looks good and you didn't have the too many defects, you got to check it against what code you're working against, but you check it against your criteria and it either passes or fails. Same thing with the wraparound bend test jig. Here's some transverse bend test samples. So these are where welds have been taken, the samples have been cut across the weld. So you can get a side bend, a couple of side bends there, a face bend, a root bend, and then you've got the longitudinal bend test specimens on the right, where you've got a face bend and a root bend. So there's a couple of different options, and this is going to be determined by the code and or your customer requirements. What are you working to? The engineer is going to set the criteria for what code and standards you're working to. And then once that's been done, you utilize that to determine, hey, is this passing or failing? Guided bend test specimen. Here's what the guided bend test apparatus looks like if you need to make one at the house, impress your wife. Or you need one at the shop or for work, or you need one. If you look in ASME Section 9 or AWSD 1.1 or any number of different codes and standards, there's a guided bend test apparatus. This is how you build one. Pretty easy to build, I would say, as far as, you're not building a rocket ship. Here's all the dimensions. But what you're doing is you're basically just taking, like I've said in previous ones, you're just looking for ductility of the weld metal. Ductility is the key. So you're just going to punch this, your guided bend sample through this mandrel, this jig / fixture, and if it cracks, you're going to have to redo it. If it bends and you don't have any defects that are outside the range of acceptability, your bend test passes. QW163 acceptance criteria bend tests. The weld and heat affected zone of a transverse weld bend specimen shall be completely within the bent portion of the specimen after testing. The guided bend specimens shall have no open discontinuity in the weld or heat affected zone exceeding 1/8 of an inch measured in any direction on the convex surface of the specimen after bending. Open discontinuities occurring on the corners of the specimen during testing shall not be considered unless there is definitive evidence that they result from a lack of fusion, slag inclusions, or other internal discontinuities. So what's this telling us? This is telling us that the weld and the heat affected zone of a transverse weld bend specimen shall be completely within the bent portion of the specimen after testing. Let's say you get this thing misaligned and your weld isn't bent. You bend a piece of the base metal, and your weld metal isn't in the bend. You got to chuck it. You got to discard that piece and start over. So you got to make sure and you get it lined up, and when it goes through, it's got to get bent. The weld's got to get bent. Just sending this through in the base metal bending does not count. The other one outlines that you can't have any open discontinuities in the weld or heat affected zone larger than 1/8 going in any direction. And if they occur on a corner, because this material is going to want to tear on a corner, if you don't get your corners a good enough radius so they don't tear, sometimes you'll have something open up on the corner. So if something opens up on the corner, it's good. You can accept it unless there's evidence that it's from lack of fusion or slag. I've gone both ways on these. I've looked at some and there's been slag in there, or lack of fusion, and you got to chuck them. You got to discard that one, fail that sample. And on other times I've had, looked at it and it was beautiful weld metal, but it tore because it was too sharp of a radius. So this is just giving your acceptance criteria, QW163. Fillet weld tests. Fillet weld test, because you can't take a tensile test on them and you can't do a bend test on them really. So you have to just destructively test them. So here's a fracture test for a fillet weld test. The stem of 4 inches, performance specimen center section, QW 462.4B, or the stem quarter section, QW 462.4C as applicable, shall be loaded laterally in such a way that the root of the weld is in tension. The load shall be steadily increased until the specimen fractures or bends upon itself, flat upon itself. This is see the word in there, performance? That's for qualification of people. The other ones where you do for fillet weld tests is you would take a slice out of them and then macro etch it. You'd throw some type of acid on there that would bring out and show you that if you got complete penetration of the weld. So that's fillet weld testing is a little different than groove weld testing just due to the configuration and the geometry. You can't get a tensile test out of it and you can't get a bend test out of it. And for performance qualification for fillet weld tests, this is how you destructively test them. QW170 notch toughness tests. Charpy V-notch. General Charpy V-notch impact tests shall be made when required by referencing code. So ASME Section 9 doesn't require notch toughness tests, but if you're working to a code that has cryogenic applications or whatever reason, that code like B31.1, B31.3, or Section 1, which is boilers, if that section of the code, that construction code says, hey, you need to do Charpy V-notch impact tests, then you'll come and do this section. When not specified by the referencing code, the test procedures and apparatus shall conform to the requirements of SA 370. So if you go to SA 370, that's going to tell you how to do it. But generally, you don't do notch toughness testing unless the engineer calls it out, the qualifying code calls it out, or the construction code that you're referencing calls out this notch toughness testing. Notched bar testing. Charpy's the most common, and IZOD is also in there. Measures resistance to sudden impact, notch toughness. Results used for comparison. Specimens are usually chilled to Here's one you're going to run across a lot as a CWI. The Charpy V-notch test. The Charpy V-notch test employs a square bar 55 millimeters by 10 millimeters by 10 millimeters with a 2 millimeter deep notch on one side. The test apparatus has a swinging pendulum that is released from a specified height, striking the specimen at the bottom of the pendulum swing. The test specimen is fractured, absorbing energy, which slows down the pendulum. The pendulum such that it does not swing up as high as it would on a free swing, i.e. no specimen in the holder. A calibrated scale on the apparatus converts the height of the pendulum swing to the energy absorbed by the breaking specimen in foot-pounds. Low alloy steels exhibit a ductile to brittle transition with decreasing temperature. It should be noted that tests are usually performed in triplicate because of the scatter in the test results. Here's a Charpy V-notch test samples, courtesy of Uncle Sam again. It shows you the size of them. They're 10 millimeters. You put a machined groove into the test sample, the test specimen, and then this, tells you how it's going to react if there's a crack of that size in a specific material. And then these are usually the code that you're working to or the customer requirements are going to tell you what temperature that they want the Charpy V-notch test done at. Do they want it done at 40 or do they want it done at minus 40? Then you cool the test samples down to the appropriate temperature and you put it in a test apparatus and you hit it with that hammer and it gives you the impact strength of the material. And like I've said before, you don't just do one impact test, you do multiple impact tests because the scatter of the data that you receive can be a little weird. And I mean weird, you might have one test sample that's just nowhere close to what the others are. So that's why you do multiple tests. Charpy V-notch test. You can see how you take your specimen after it's cooled to whatever temperature and you put it in the anvil and you can see where the striking edge of the pendulum hits on the opposite side of the specimen from the notch that you've machined into the test specimen, and you have the starting position of the pendulum, the striking edge, it comes down, it whacks that test specimen, and in whacking that test specimen, the test specimen absorbs an amount of kinetic energy, impact energy from that hammer. So then the pendulum and the hammer only go up a certain distance. Well, you measure that distance and that tells you how much impact energy the test specimen was able to absorb. And you do this on multiple test specimens, not just one, because I keep preaching this, but it's because the data that you receive from just one test specimen is probably, there's a good chance that it's out of the ballpark. So if you based your decisions on one test specimen, you wouldn't be getting a good answer. You might be, but there's a reason why they do these things in multiples of 3 or more. Fracture toughness test, the significance. It provides a measure of resistance to crack initiation or propagation or both. The same welding process, procedure, and weld cooling rates must be used for the test sample and the structure. Fracture toughness of steels is sensitive to service temperature. Service temperature is a biggie. There's a thing called the ductile to brittle transition temperature in the iron carbon system, and the way a steel reacts at 89 degrees in the West Texas sun is not the same way that steel is going to react in Alberta in January when it's minus 35 degrees Fahrenheit out. That same steel that is tough as hell in the West Texas sun is going to shatter like glass in northern Alberta in January. I keep bringing this up, but it can't be downplayed. People wonder what's going on and why they don't have cracking in Montana or North Dakota or Alberta. Oh, this steel was good when we were using this during the summertime, and now this steel's suddenly gone bad. No, it's all related to the service temperature. Steels are very sensitive to service temperature, and that's why we want to know what the fracture toughness of a steel is at a given temperature. Here's a fracture toughness test, apparatus, Charpy V-notch test. You can see the placement of the specimen in the anvil, waiting for the hammer to get let go and introduce the kinetic energy, the impact energy into that part. Specimen. Then you measure how much energy the specimen absorbed, and that tells you how tough the material is. You do this at various temperatures. Generally, the code or a customer requirement will tell you what your impact strength needs to be at what temperature. Somebody doing work in West Texas is probably not going to have the same impact test requirements as somebody that has work going on in northern Alberta in the middle of January. So these are things you need to keep in mind in regards to impact toughness, the Charpy V-notch test, the fracture toughness of a material. And you also need to keep in mind that you don't just do one impact test specimen. You do 3, or depending on what the customer or code requirements are, you do multiple tests, because you can have one test that is just absolutely screwy, absolutely out there from a numerical or a mathematical standpoint. So it gives you a better set of numbers if you do multiple impact tests, multiple specimens. Another fracture toughness test specimen, like I said, the Charpy V-notch test, impact test specimens. Length is 55 millimeters, and then they're 10 millimeters by 10 millimeters, and then the groove is a couple millimeters deep, and there's the details of the notch. You've got a 25 millimeter radius in the bottom. It's a 45-degree angle. You do multiples of these, and you put them in a vat or a container to get it to the temperature, the test temperature that you're looking for. You get it to that test temperature and you test it, you break it. The hammer hits the side opposite of the notch. The fracture toughness is then measured by the amount of impact energy that the test specimen absorbs. You do multiples of these and it'll give you an idea of the fracture toughness of your material. QW190, other tests and examinations. QW191 covers radiographic examination, which is shoot an X-ray through the weld to see if there's any defects or discontinuities that could be an issue. Discontinuities not necessarily, but defects, yes. It's like getting an X-ray on your arm, or an X-ray on, you break your leg and they shoot an X-ray on it to figure out if you got a broken leg. Pretty much the same thing, except they're shooting the welds, shooting the X-rays through some welds. Ultrasound, I think pretty much everybody's probably got a pretty good idea of what ultrasonic testing is. Instead of going in and looking for a problem with your liver or your heart, or to see if a woman's pregnant or check the sex of the baby, the gender of the child, here you use ultrasonic examination to find defects on the insides of welds. You're bouncing sound waves in there. They're going down and getting kicked back, and if there's any kind of defects, it's going to show up on the screen. So these two examination methods are covered in QW 191.1 and 191.2. QW 191 radiographic examination. This is the paragraph that sets the table that is the foundation for radiographic examination for using radiography to test welds, to see if they're in compliance with the criteria that's set forth. It's technology's been around 100 years. You use a source to produce radiation. It goes through the metal. You got a piece of film on the backside and it's going to tell you on the backside that it's the film, if something's going to show up. It's like shooting an x-ray of your arm or leg, or if they're checking your spine for scoliosis, or x-raying your ankle to see if it's broken. Same theory, but you're just looking at welds to make sure there's nothing left in the weld, like a slag inclusion, or maybe you got porosity or cracking or some other type of defect in your deposited weld metal. QW 191.2, this is going to outline what needs to be done to utilize ultrasonic examination in welder performance qualification and procedure qualification. You know, ultrasonic testing, you're bouncing sound waves into a material. It's going to hit a defect, and then it's going to bounce back, and it's going to show up on the screen as a defect. Just old technology. I want to say 50, 60 years old, but shouldn't be anything new to anybody. But this gives you an idea of what ultrasonic examination does. I'm not going to do a deep dive into the non-destructive testing methods. I'm not an expert on them. I have a general idea of what they are and how they work, but not my gig, not my main focus. Just another slide. I find these slides in these military handbooks, and I feel compelled to use them. Here's, you know, a couple of different methods where they're scanning some welds. I don't know if this is necessarily relevant to what we've got going on with ASME Section 9, but it gives you a general idea on how they would scan a weld, you know, during a welder qualification or a procedure or performance qualification.
Stud welding guns. This is a variation of arc welding in which studs are welded to a plane surface automatically. The stud, which may be plain or threaded bar, if plain it will have a head, is the electrode, and it is held in the chuck of the welding gun, which is connected to the power supply. The stud is first touched onto the surface of the steel plate or section. When the current is switched on, the stud is moved away automatically to establish the arc.
QW 192 covers stud weld tests. Stud weld test is, you know, you shoot a shear stud onto a piece of base metal. It's used a lot in structural, on bridges is where I've really encountered it a lot, but I think there's a lot of it that happens on pressure vessels too. I haven't really dealt with it too much in regards to pressure vessels, more in regards to the structural applications, but obviously somebody does stud welds because there's stud weld tests that have to be done here in QW 192. Here's a stud welding gun for those of you that aren't really familiar with stud welding. I had this slide from another presentation I gave. You've got a gun, you put a stud in it, you've got a little ceramic ferrule on there. This gun is hooked up to a power supply. You push this down, you pull the trigger, it activates it and shoots the stud onto the material.
In this slide we can see the stud welding sequence. If you go to step 1, the gun is properly positioned and the main gun spring is partially compressed. You've got your ferrule in place, you've got the stud, it's held in the chuck, and at the very bottom of that stud in step number 1, there's a little gob of flux. It's like the flux that you would use on flux cord arc welding or shielded metal arc welding. It's just a little gob of flux. So you've got everything properly placed. You're going to shoot that stud where you want it to go. The trigger is pressed and the stud lifts off the work. An arc is created and melts the stud and the parent metal. So you've created this arc just like in shielded metal arc welding, and you've got a little liquid weld metal pool, but it's all contained inside that ferrule. Remember I was talking about the ferrule is kind of a little mold or a little Dixie cup that holds the liquid in place? That's what we've got going on here. The stud welding sequence doesn't work if you don't have that ferrule holding that liquid weld metal in. So then, after the arc is complete in step 3, the main spring, there's a spring in this weld gun, it plunges the stud into the molten weld pool. And once again, all your liquid weld metal is contained by that ferrule. So when you get to step 4, when the gun is taken off from the welded stud, the ferrule is broken away and discarded. It just turns into dust. You've got a weld all the way around that should look pretty much like the shape of the ferrule. So it'll look like a little itty bitty fillet weld all the way around there, but it's 100% all the way across this, the weld of the stud. So that's the nice thing about stud welding, and you can do these things by the thousands, depending on what your setup is. I think the automotive industry uses a lot of them for clips, little different kinds of clips. I used to work for a hydraulic cylinder outfit that would put the ports on the sides of hydraulic cylinders. They'd stud weld them on, and then they'd come in later with a drill and drill through the port, but it was already threaded, so it was just 90 degrees. So they could just crank these out as opposed to hand welding them. You know, if you've got to hand weld these on, it'll take you a million years. Whereas with stud welding, it's like seconds, just chunk, 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 chunk. Especially if you've got it set up, the machine's running good, and you got a guy that knows what's going on. If you had to hand weld these, it'd take you a long time. Huge savings in cost and labor and man hours for stud welding versus hand welding.
QW 195 liquid penetrant examination. This is the paragraph that covers liquid penetrant examination. QW 195.1, the liquid penetrant examination in QW 214 for corrosion resistant weld metal overlay shall meet the requirements of Section 5, Article 6, the acceptance standards of QW 195.2 shall be met. Well, I'm not going to go into this, but this lays out and gives you the criteria and where you need to go for liquid penetrant examination, how to do it, all that stuff. Liquid penetrant examination, you spray a dye on a part. You let it dwell for a bit. You spray on some developer. That's after you've wiped off the excess dye, and then that's going to draw out the dye. And if you have any defects or discontinuities, they'll show up on your surface, and then you're going to make a determination on whether or not that piece has passed, if it's met your acceptance criteria. Liquid penetrant examination. This is for corrosion resistant overlay. Corrosion resistant overlay is when you have a situation where you have a very acidic or corrosive medium, let's say an acid or something like that, and you have a vessel, but you can't afford to have the whole thing made out of a nickel alloy or a stainless steel. So a lot of times people will build the vessel out of carbon steel, which would be your base material, and then it has all your structural elements are in that, and then you have your corrosion resistant overlay. So that would contain the corrosive medium. And so to get everything within the code, you're going to need to follow the acceptance criteria of QW 195.2, and you need to meet the requirements of Section 5, Article 6. But liquid penetrant examination, I haven't done it very much. I've only done it a handful of times for corrosion resistant overlay type situations. Regular, your standard run of the mill carbon steel or stainless steel pressure vessel applications, you generally don't have to do a liquid penetrant examination. This is generally for corrosion-resistant weld metal overlays. QW196 covers resistance weld testing. I haven't dealt with this very much either, but it's out there, it exists. You're basically taking 2 electrodes and a couple of little thin pieces of sheet metal. You put your 2 electrodes on either side of it, sends a bunch of electricity through there, and you end up having, making a spot weld or a little spot resistance seam weld. I'm not very well versed in the resistance welding vocabulary, but I know it exists and I could probably read up on it. But just realize that if you have to do resistance weld testing, QW196 is where you go. QW197 covers laser beam welding. I haven't ever dealt with this, but laser beam welding is just like it sounds. You got a laser beam and you use it to make a weld with 2 pieces of material. So if you got that going on and you're in an industry where you have laser beam welding to ASME Section 9, QW197 is the paragraphs that's this is the area of the code that's gonna drive what you've got going on. So this is a summary of Article 1, Welding General Requirements. In this PowerPoint presentation, we talked about impact testing, bend testing, tensile testing, mechanical testing, and just a hodgepodge of other information that's located in Article 1, the welding general requirements. So this is going to set the table. So now my next one is going to be into Article 2, which will be procedure qualification. So that'll be a little different animal, but this YouTube video and the previous one, these are the ones that set the table for where we're going to go next, which is into Article 2, which has procedure qualification and what we need to go through there. Questions, comments, here's my address, email address. I'm out of Katy, Texas. I do welding, procedure qualification, and consulting. If you got any questions, this is how you track me down. Thanks. Bye.